Hello, welcome back. Wherever you are tonight, and I find myself genuinely curious about that, what kind of night it is where you are, whether it's raining or still or lit by a moon you can see from where you're lying, I'm glad you made it here. Maybe the day was ordinary in all the ways that ordinary days are secretly exhausting. Maybe it was something else. Either way, you've arrived, and this is a good place to have arrived at. Go ahead and settle. Not the preliminary settling, the kind where you're still holding yourself slightly in readiness, but the final kind, the deliberate, conscious decision to be where you are. Let the mattress or the cushions or whatever is beneath you take the full weight of everything you've been carrying. Let your shoulders drop. Let your breathing slow. The words will come in at the pace that suits you tonight, and if you drift before the end, that is precisely what we're here for. You don't need to retain any specific number or equation or technical term. If something stays with you, it will stay because it attached itself to something you already cared about, not because you worked to hold it. This is how the best learning happens, not through effort, but through resonance. If you're here for the first time, welcome, this is Late Space. We take big ideas at the pace of a long, quiet evening. If you find yourself wanting to come back on other nights like this one, a gentle like or subscribe helps other people who need somewhere like this find their way here too. Do it later, or not at all. For now, just breathe. Tonight we are going to sit with a question that sounds simple and is in fact one of the hardest questions in all of physics and engineering. How do you get to the nearest star? Not the nearest star as an abstraction, not as a poetic gesture toward the infinite, the literal, actual, specific nearest star to our Sun, which is a red dwarf called Proxima Centauri, located 4.24 light-years from Earth in the direction of the southern constellation Centaurus. A star that has a planet in its habitable zone. A star that, as of July 2025, has 3 known planets orbiting it, at least one of which is roughly the size of Earth and sits at the right distance for liquid water to potentially exist on its surface. That star. That specific star. The closest one. The one that, if any star in the galaxy should be within reach, should be this one. And the answer to the question, the honest, current, fully worked out answer to how you would get there, is that it is nearly impossible. Not romantically impossible, not the kind of impossible that means very difficult and requiring great effort. Nearly impossible in the precise physical engineering sense that the obstacles are not primarily ones of ambition or resources or political will, but of physics itself, of what matter can do, what energy costs, what time means, what the interstellar medium does to anything that moves through it, and what it means for a human being, or any machine. To cross a distance so vast that even light takes more than 4 years to make the journey. We are going to go through it honestly tonight. Not to be discouraging, there is something clarifying, even comforting, about understanding the true shape of a hard problem. And not to suggest the attempt isn't worth making, it is, perhaps, the most important thing our species could attempt in the long run, but to honour the reality, which is more interesting than the simplified version most people have encountered. Close your eyes when you want to. Let's begin. Let's start with the distance, because everything else follows from the distance, and the distance is the first thing that needs to be felt rather than merely stated. 4,024 light-years. A light-year is the distance light travels in 1 year, not a unit of time, though it's easy to confuse it for one, but a unit of distance. Light travels at approximately 299,792 kilometers per second. In 1 second, it covers a distance of nearly 300,000 kilometers. In 1 minute, it covers about 18 million kilometers. In 1 hour, about 1.08 billion kilometers. In 1 day, about 26 billion kilometers. In 1 year, about 9.46 trillion kilometers. 1 light year, 9.46 trillion kilometers. 5,088 trillion miles. 4.24 light-years, roughly 40 trillion kilometers, 25 trillion miles, a number so large that the word trillion begins to lose its bite, becomes just a sound rather than a quantity. Let me try another approach. The farthest human-made objects from Earth are the Voyager spacecraft, which we discussed in a recent episode, old friends at this point, still transmitting, still moving. Voyager 1 is about 24 billion kilometers from Earth as of 2026, traveling at roughly 17 kilometers per second. It has been traveling for nearly 50 years. At Voyager 1's current speed, it would take approximately 74,000 years to reach the distance of Proxima Centauri. 74,000 years. An amount of time longer than anatomically modern humans have been making art. An amount of time longer than the entirety of recorded human history, multiplied by roughly 15. An amount of time in which every language currently spoken on Earth would have been replaced by descendants we couldn't recognize. An amount of time that makes the entire span of human civilization, from the first cities to the present, look like a single afternoon. Voyager 1 is the fastest large object humanity has ever launched, and it would take 74,000 years. This is the foundational problem of reaching Proxima Centauri. Everything else we're going to discuss tonight, the engineering challenges, the physics obstacles, the proposals and their limitations, all of it is downstream of this. The distance is simply enormous, and our fastest current spacecraft would need a span of time that exceeds the entire history of our species to cover it. Now, to be fair to the dreamers and the engineers who have thought about this seriously, nobody proposes going at Voyager's speed. Voyager wasn't designed for interstellar travel. It was optimized for planetary encounters within our solar system. And its speed reflects what was achievable with 1970s technology using a gravitational assist from the outer planets. The question is not whether we could go faster. We obviously could. The question is how much faster, and what it costs to get there, and what new problems emerge at higher speeds, and whether any of those problems are soluble with any technology that is physically possible rather than merely scientifically speculative. Let's talk about chemical rockets first, because that's what we actually know how to build and operate. The Space Shuttle's main engines, burning liquid hydrogen and liquid oxygen, produced exhaust velocities of about 4.4 kilometers per second, meaning the propellant left the engines at that speed, and the reaction pushed the vehicle in the opposite direction. Modern spacecraft use variants of this basic approach: chemical propellants, combustion, exhaust, thrust. The theoretical maximum exhaust velocity for any chemical rocket, the speed at which the combustion products leave the nozzle, set by the energy available in the chemical bonds being broken and reformed, is around 5 kilometers per second. No matter how cleverly you engineer the nozzle or how efficiently you run the combustion, you can't exceed the energy content of the chemical reaction, and that energy content sets a firm ceiling. To reach Proxima Centauri in, say, 1,000 years, which would still be longer than any current human institution has survived, but which is at least in the range of a sustained civilizational project, you would need to travel at roughly 0.4% of the speed of light. That's about 1,300 kilometers per second. For a chemical rocket to reach 1,300 kilometers per second, you need to apply the Tsiolkovsky rocket equation, which is the fundamental constraint on all rocket propulsion. The equation relates the final velocity of a rocket to the exhaust velocity of its propellant, and the ratio of the rocket's initial mass to its final mass. If the exhaust velocity is 5 kilometers per second, and you want to reach 1,900 kilometers per second, a velocity 260 times the exhaust velocity, the equation demands a mass ratio that is approximately e to the power of 260. E to the power of 260 is not a number you can write out in this script, or in this book, or in any physical object that could exist in the universe. It is a number so large that the total number of atoms in the observable universe is negligibly small by comparison. You would need a rocket whose initial mass was this incomprehensible factor times greater than its final mass. Chemistry cannot get you to Proxima Centauri. Not in any reasonable time frame. Not in any unreasonable time frame that the words any time frame can accommodate. Wherever you are, I hope you're comfortable, we've established the foundation. Let's keep going. Nuclear propulsion is the next category, and it's where things start to become more interesting and more complex simultaneously. In the 1950s and early 1960s, the United States ran a program called Project Orion, which proposed something genuinely extraordinary, a spacecraft propelled by nuclear explosions. The ship would carry a large supply of nuclear bombs, initially fission, potentially later fusion, and detonate them behind the spacecraft, one by one, with the pressure pulse of each explosion pushing the vehicle forward through a large shock absorber plate called a pusher plate. The concept was not insane. It was worked out in considerable engineering detail by people including Freeman Dyson, one of the most creative physicists of the 20th century, and Ted Taylor, a brilliant weapons designer who devoted his later career to disarmament. The specific impulse, the efficiency measure of a rocket, essentially the exhaust velocity in appropriate units, achievable with nuclear pulse propulsion, is dramatically higher than for chemical rockets. Not by small factors, but by factors of hundreds. Project Orion designs were capable, on paper, of reaching velocities of perhaps 3 to 5% of the speed of light with a sufficiently large vehicle. At 3% of the speed of light, the journey to Proxima Centauri would take about 140 years, still longer than a human lifetime, but in the range of a multi-generational mission. A ship launched today, arriving in the era of our great-great-great-grandchildren. Project Orion was cancelled in 1963, primarily because the Nuclear Test Ban Treaty made atmospheric testing of nuclear devices illegal, and the project depended on being able to test the concept before scaling it up. The political conditions that led to the Test Ban Treaty, the global recognition that atmospheric nuclear testing was poisoning the biosphere with radioactive fallout, were good conditions to have reached, and the loss of Orion was a reasonable price for the gain in human safety and sanity represented by the treaty. A successor design, Project Daedalus, was developed in the 1970s by the British Interplanetary Society as an engineering study of an unmanned interstellar probe powered by nuclear fusion, specifically the fusion of deuterium and helium-3, which produces a high-energy plasma exhaust without the fission bomb complications of Orion. The study was remarkable for its rigor, a genuine attempt to design an actual spacecraft using known physics and near-term plausible technology. The Daedalus vehicle was enormous, a two-stage craft with a total initial mass of roughly 54,000 metric tons, the vast majority of it fuel, and would have been capable of reaching Barnard's star, about 6 light-years away, in about 50 years. The problem with Daedalus was not primarily the physics. The physics worked, within the constraints of the design. The problem was the fuel. The Daedalus design required 30,000 metric tons of helium-3, an isotope that is extraordinarily rare on Earth. The total amount of helium-3 available on Earth is measured in kilograms. The Moon has more, deposited by the solar wind over billions of years, but even the Moon's helium-3 reserves are estimated at perhaps 1 million tons total, and extracting them would require industrial mining operations on a scale that doesn't exist and would take centuries to establish. The outer planets, particularly Uranus and Neptune, might have far larger reserves in their atmospheres, but accessing them would require infrastructure that is generations beyond our current capability. Daedalus established that nuclear fusion propulsion is physically sound in principle. It did not establish that it is practically achievable in any near-term time frame, because the fuel problem is not a small engineering challenge, but a civilizational scale resource mobilization problem. Let me tell you about the most audacious, serious proposal that has been made for reaching Proxima Centauri in a human-relevant time frame. It was announced in April 2016, with considerable fanfare, by the billionaire Yuri Milner, the physicist Stephen Hawking, and the entrepreneur Mark Zuckerberg. It was called Breakthrough Starshot, and it proposed to do something entirely different from any previous approach. Instead of pushing a large spacecraft with nuclear propulsion, Breakthrough Starshot proposed to send a very small spacecraft, a nanocraft, essentially a computer chip the size of a postage stamp, and push it not with a propellant exhaust but with a laser beam. A very powerful laser beam shining from Earth on a tiny reflective sail attached to the nanocraft, accelerating the whole system through radiation pressure to a significant fraction of the speed of light. The idea has genuine physical merit. Radiation pressure is real. It's the force that light exerts on any surface it strikes, the same effect that causes comets' tails to stream away from the sun. A reflective surface struck by a powerful laser can be accelerated by the momentum transferred from the photons. The advantage is that the propellant, the photons, stays behind. You don't need to carry your fuel. The laser array on Earth provides all the push the tiny spacecraft needs. The proposed laser array would generate about 100 gigawatts of power, roughly 10 times the total power output of the Hoover Dam. It would be focused on the nanocraft sail with extraordinary precision. In a few minutes of illumination, the nanocraft would be accelerated to 20% of the speed of light. At that speed, the journey to Proxima Centauri would take about 20 years. A signal confirming arrival would take another 4.24 years to travel back to Earth. Within perhaps 30 years of launch, we could have our first close-up look at the Proxima Centauri system. It's a beautiful idea. And in September 2025, Scientific American reported that the project was on indefinite hold. The reasons for Starshot's stall illustrate, with specific engineering clarity, the gap between a physically sound concept and a practically achievable one. Let me go through the problems, because each one is instructive. The first problem is the laser array itself. A 100 gigawatt laser array is not a technology that currently exists. The most powerful laser arrays ever built for any purpose, including the National Ignition Facility's fusion experiments, which use laser arrays to compress fusion targets, reach into the megawatt range in sustained operation, perhaps higher in brief pulses. A 100 gigawatt array is a factor of roughly 100,000 more powerful than anything we've built. Building it would require a manufacturing and electrical infrastructure that simply doesn't exist, and the cost estimates for the full system have run into the tens of billions of dollars, with most of the optimistic estimates assuming technology learning curves that may or may not materialize on relevant timescales. The second problem is pointing. The nanocraft, traveling at 20% of light speed, needs to be illuminated by the laser for the entire acceleration phase, which lasts a few minutes. During this time, the craft is moving extremely rapidly, and the beam needs to track it with extraordinary precision. The beam also needs to be focused to a spot size matching the sail, a few meters across, from a baseline of the Earth's surface, which means compensating for atmospheric turbulence, maintaining coherence across the array's entire multi-kilometer aperture, and managing any slight misalignments in the phased array of lasers. Each of these is a genuine technical challenge. None is physically impossible, but the combination is demanding in ways that have not yet been solved even in prototype form. The third problem is the sail. The sail needs to be thin enough to be very light, a few grams for the entire craft, and reflective enough to survive the laser irradiation without absorbing too much energy and burning up. The power per unit area hitting the sail during acceleration is enormous. At 100 gigawatts focused on a few square meters, the irradiance is beyond anything any material currently survives while remaining structurally intact and highly reflective. Research on silicon nitride films and other materials has made progress. There are now photonic crystal mirrors with 99% reflectivity and sub-microgram masses that didn't exist a decade ago. But scaling these from laboratory demonstrations to a functional, launchable sail remains a substantial engineering gap. The fourth problem is the interstellar medium. Between here and Proxima Centauri, space is not perfectly empty. It contains dust grains, microscopic particles of carbon, silicates, and other materials, dispersed at very low densities. At 20% of the speed of light, these dust grains become lethal projectiles. Not lethal in the Hollywood sense of explosions and flames, but lethal in the practical sense. A single dust grain 1 micron in diameter, striking the nanocraft at 60,000 kilometers per second, delivers an energy impact equivalent to a small bullet. Over the course of a 4 light-year journey, the nanocraft's frontal cross-section will be struck by many thousands of such particles. The cumulative erosion will gradually ablate the surface of the spacecraft and potentially destroy its delicate electronics and sensors. Estimates suggest that across the journey, each square centimetre of the craft's frontal area will experience about 1,000 impacts from particles larger than 0.1 microns. A 1 micron particle striking at 20% of light speed hits with roughly the same kinetic energy as a bullet. There are proposed mitigation strategies heavily shielding the front face, designing the nanocraft to be as cross-sectionally narrow as possible, perhaps using a sacrificial ablative shield. But none of these has been demonstrated to solve the problem at the required scale. The fifth problem is communication. The nanocraft, upon arriving at Proxima Centauri, needs to send its data back to Earth. It has perhaps a gram of mass for everything: sensors, computer, power supply, and communication system. The nearest star is 4.24 light-years away. Transmitting a useful signal from a gram-scale device across 40 trillion kilometers, with a transmitter running on whatever power the craft can generate from a tiny solar panel at a star that is already dim to a receiver on Earth. This is a signal engineering challenge of extraordinary difficulty. The required antenna size, the transmission power, the data rate achievable, the error correction needed for a signal that has travelled 40 trillion kilometers, all of these press against fundamental physical limits. Philip Lubin, the physicist at UC Santa Barbara, whose work on directed energy propulsion was central to the Starshot concept, estimated that by 2025 breakthrough had spent about $4.5 million of the proposed $100 million on research, funding about 30 contracts exploring different aspects of the problem. The results were scientifically productive, better laser materials, better photonic sails, better understanding of the interstellar medium. But the gap between the research state and a functional system remained enormous. Starshot is not dead. Its technical contributions to photonics, materials science, and laser engineering have genuine value for other applications. The problems it identified are real research frontiers, and the concept itself, laser-propelled light sails accelerated to a fraction of light speed, remains the most physically plausible approach to reaching another star in a human-relevant timeframe that anyone has seriously proposed. But as of September 2025, it is on indefinite hold. The engineering challenges that seemed like they might yield to sustained effort and investment have proven more stubborn than the optimistic projections of 2016 suggested. Wherever you are, I hope you're comfortable. Let's breathe here before we continue. I want to make sure this feels like what it is, not a litany of failure, but an honest reckoning with the true difficulty of a true problem. The people who have thought hardest about interstellar travel are not naive optimists who haven't considered these obstacles. They are serious scientists and engineers who have spent careers quantifying exactly how hard it is, and who have found that it is harder than the public conversation usually acknowledges. That honesty is itself a kind of achievement. Knowing the true shape of a hard problem is the prerequisite for solving it, or for knowing which parts of it might be solvable on what timescales. The history of technology is full of problems that seemed impossible until a specific breakthrough, a new material, a new energy source, a new physical insight changed what was possible. It's also full of problems that remained impossible for longer than optimists projected, because the physical constraints turned out to be more fundamental than hoped. Interstellar travel sits in this space of genuine uncertainty. Not impossible in principle. Extremely difficult in practice, requiring advances in multiple independent technologies simultaneously, each of which has a speculative timeline. The only honest answer to when could we reach Proxima Centauri is, we don't know, and anyone who gives you a specific date is making assumptions that current evidence doesn't support. Let me tell you about a problem that doesn't get discussed as often as the propulsion problem, but is, in some ways, equally fundamental. Even if you could accelerate a large spacecraft to a significant fraction of the speed of light, let's say 10%, which is already far beyond anything we've demonstrated or have a clear path to achieving, you would face the problem of deceleration. The journey to Proxima Centauri at 10% of light speed takes about 42 years one way. If you want to actually stop at Proxima Centauri, to orbit it, to study it, to send down any kind of probe, you need to slow down by exactly as much as you sped up. You need to decelerate from 10% of light speed to 0, which requires the same energy as accelerating from 0 to 10% of light speed. The Tsiolkovsky equation applies just as brutally to deceleration as to acceleration. If you're carrying your deceleration fuel with you when you launch, because there's no laser array at Proxima Centauri to push back against, then you need to carry enough propellant to first accelerate the spacecraft, then accelerate all the deceleration fuel, then decelerate with the deceleration fuel. The fuel requirement multiplies catastrophically. This is why the breakthrough Starshot design was a flyby, not an orbiter. The nanocraft would flash through the Proxima Centauri system at 20% of light speed, taking measurements and images in a window of perhaps a few hours before moving on. There is no feasible way to stop it. Stopping requires either a deceleration mechanism at the destination, a laser array at Proxima Centauri pushing back against the approaching spacecraft, which would need to be built before you go, which means you need a way to build it without going there first, which is a chicken and egg problem of extraordinary circularity, or carrying enough fuel to decelerate, which multiplies the mass budget to the point of impracticality even for fusion-powered designs. A clever proposed exception to this exists, developed by Ren Heller of the Max Planck Institute. His idea is to use the radiation pressure of Proxima Centauri itself, the star's own light, to decelerate the sailcraft as it approaches. The craft would be designed to flip its sail to face the approaching star and let the starlight push back against its incoming momentum. In principle, if the sail is large enough and the approach geometry is right, this could achieve enough deceleration to actually enter orbit around the system, rather than just flying through it. The numbers are challenging. The deceleration force from Proxima Centauri's light, a dim red dwarf, much less luminous than the Sun, is small. The sail would need to be very large and very reflective to use this force effectively. And the approach trajectory needs to be precisely calculated so that the craft passes close enough to the star for the radiation pressure to be significant without being destroyed by the radiation field. But the physics works, in principle, and it's one of the more elegant proposed solutions to the deceleration problem. Let me tell you about what awaits at the destination, assuming we somehow manage to get there. Because the target of all this effort is not merely a star, it is a star with planets, one of which has some of the properties that make scientists think about the word habitable. Proxima Centauri b was announced in 2016, detected through the radial velocity method, the tiny wobble the planet's gravity induces in its star as it orbits. The planet has a minimum mass of about 1.3 times Earth's mass, minimum because radial velocity only measures the component of the star's wobble along our line of sight, and if the planet's orbit is inclined relative to us, the actual mass is higher. It orbits Proxima Centauri at a distance of about 0.048 astronomical units, roughly 7 million kilometers, completing one orbit every 11.2 days. At that distance from such a dim star, Proxima b receives about 65% of the stellar energy that Earth receives from the Sun. In terms of raw energy budget, it sits in the zone where liquid water could in principle be stable on a rocky surface, given the right atmospheric conditions. The if is enormous. The first and most urgent question is whether Proxima b has an atmosphere at all. Proxima Centauri is a red dwarf star, and red dwarfs are energetically violent, particularly in their youth. They produce powerful ultraviolet and X-ray flares, bursts of high-energy radiation that can be far more intense than anything the Sun produces, relative to the normal stellar brightness. Proxima Centauri flares frequently, and these flares could have spent billions of years stripping away any primordial atmosphere Proxima b might have had. Whether the planet maintained an atmosphere through this bombardment, or whether it was stripped to a barren vacuum, depends on factors we don't yet know, the strength of the planet's magnetic field, the rate at which geological outgassing replenished any lost atmosphere, the precise history of flare activity over the billions of years the planet has existed. Some models suggest an atmosphere could survive if the planet has a strong enough magnetic field. Others suggest the stellar environment is too hostile for any atmosphere to persist. As of 2026, we have not detected an atmosphere on Proxima b. We have not yet been able to, with existing instruments. The planet doesn't transit its star from our vantage point, or transits are extremely unlikely, with only about a 1.5% geometric probability, which means we can't use the transit spectroscopy technique that Webb has applied to planets like TRAPPIST-1e. Direct imaging of Proxima b is at the very edge of what the next generation of large telescopes might be able to achieve. There is also the question of tidal locking. At 0.048 AU from its star, Proxima b almost certainly rotates synchronously, one side permanently facing the star, the other permanently in darkness, the same face always lit the way the moon always shows us the same face. A tidally locked planet has a dramatically different climate regime from Earth. A permanent day side where temperatures can be extreme, a permanent night side where temperatures can be extreme in the other direction, and a narrow band around the terminator, the boundary between day and night, where temperatures might be moderated enough for liquid water. Whether a tidally locked planet can maintain a stable, habitable environment is contested. Some atmospheric circulation models suggest that a thick enough atmosphere could redistribute heat efficiently enough to keep temperatures moderate over a wide area. Others suggest the atmospheric redistribution is insufficient, and the temperature extremes would make the planet largely uninhabitable. The answer depends on the specific atmospheric composition, the greenhouse effect, the cloud patterns, none of which we currently know for Proxima b. Proxima d, the smallest of the 3 known planets in the system, confirmed by the NERP spectrograph in July 2025, has a mass smaller than Mars. It orbits much closer to the star, well inside the habitable zone, and is likely too irradiated to be hospitable by any plausible physical scenario. Proxima c, if it exists, its status remains disputed, orbits far outside the habitable zone, far too cold for liquid water, even with a generous greenhouse effect. The Proxima Centauri system is the closest star system to our own. It contains the closest known habitable zone exoplanet. And despite that proximity, we know remarkably little about whether any of its planets are actually habitable. Let me tell you about something called the rocket equation as a philosophical object, not just a physical constraint. Because I think there's something worth feeling in the specific way the Tsiolkovsky equation makes interstellar travel hard. The rocket equation, derived by the Russian mathematician and rocket pioneer Konstantin Tsiolkovsky in 1903, is simple in form and devastating in implication. It says that to change the velocity of a rocket by a certain amount, you need a fuel-to-dry mass ratio that grows exponentially with that velocity change divided by the exhaust velocity. Exponential growth is the mathematical structure that defeats most human intuitions about scale. When something grows exponentially, it doesn't grow steadily, it starts small, then suddenly explodes beyond any scale you were imagining. The famous example is a lily pad doubling every day on a pond. On day 29, the pond is half covered. On day 30, it's completely covered. The growth looks modest until suddenly it doesn't. The rocket equation is exponential in the other direction. Not exponential growth of what you can achieve, but exponential growth of what you need to achieve it. Double the velocity you want to reach, and the fuel requirement doesn't double, it squares. Keep doubling the velocity, and the fuel requirement climbs toward numbers that have no physical realization, because there isn't enough matter in the solar system to build the rocket. This is why interstellar travel is not simply a very long version of what we already do. It's categorically different in difficulty, not just quantitatively different. Going from chemical rockets to nuclear propulsion doesn't escape the rocket equation, it changes the exhaust velocity, which shifts when the exponential growth starts to bite, but doesn't eliminate the exponential growth. only by abandoning rockets entirely. By using lasers to push a spacecraft that carries no propellant, do you escape the rocket equation's grasp. But then you face the deceleration problem, and the laser power problem, and the targeting problem, and the dust problem, and the communication problem. The universe has arranged its distances so that the nearest interesting destination requires a spacecraft that is either extraordinarily large to carry the necessary fuel or extraordinarily small to be pushed by a laser. Neither option is comfortable. Neither option is currently practical. Both options are physically possible and represent genuine future engineering frontiers. The universe isn't malicious. It doesn't arrange things to frustrate us, but it doesn't arrange them for our convenience either. It simply is what it is, operating according to the laws of physics, which include the rocket equation and the finite speed of light. And we are the inhabitants of one small planet trying to figure out how to reach its neighbours. There is an idea I want to tell you about that takes a completely different approach to the problem. Not faster rockets, not laser sails, but something that sidesteps the question of getting people or even probes there physically. It's called a generation ship, and it's been part of science fiction for as long as science fiction has existed, but it has a serious engineering literature too. A generation ship would be a self-contained world, a large spacecraft, perhaps kilometers long, perhaps containing a population of thousands or tens of thousands of people, designed to be entirely self-sustaining for the centuries required to cross the distance to another star at sub-relativistic speeds. Not everyone who boards would arrive. The ship would be a society, with births and deaths and generations, the original travellers aging and dying while their children and grandchildren continued the journey. Those who arrived at the destination would be the descendants, perhaps many generations removed, of those who left. The idea has a particular emotional texture that I think is worth sitting with for a moment. Imagine choosing to embark on a journey that you know you will not complete, that your children will not complete, or their children, that the destination is an abstraction to you, a star, a possibility, a hope, because no one living when you board will see the arrival. What motivates that choice? What kind of civilization makes it? The practical problems are extraordinary. Maintaining social cohesion, technological capability, biological health, and the institutional knowledge needed to operate the ship over centuries is a challenge that has no precedent in human history. Every civilization that has ever built something intended to last centuries has eventually failed to maintain it. Libraries burn, cities fall, languages change past comprehension, and yet, looked at from a certain angle, the entire project of civilization is already a kind of generation ship. The scientific institutions, the libraries, the engineering traditions, the cultural practices that make it possible for me to discuss the physics of interstellar travel tonight. All of these were built and maintained by countless generations who never knew each other and who collectively transmitted something precious across time. Perhaps the question is not whether a generation ship is possible, but whether the will to attempt it could be sustained by the same mechanisms that have sustained every other multi-generational human project, a shared sense of purpose, a culture that honours the past while serving the future, and an understanding that the work is worth doing even if you personally will not see the end of it. This is speculation. The engineering problems of a generation ship are enormous and largely unsolved. The social and psychological problems may be even harder. But the idea locates the obstacle where I think it genuinely is for something like a generation ship, not in physics, which merely requires going slowly rather than fast, but in the human capacity for sustained multi-generational commitment to a project whose benefits accrue only to descendants. Let me tell you about what the nearest stars actually are, in physical terms, because nearest star can create a misleading impression of proximity. Alpha Centauri is actually a triple star system. The two brightest components, Alpha Centauri A and Alpha Centauri B, are both sun-like stars, forming a binary pair that orbits each other with a period of about 80 years at a typical separation of about 23 astronomical units. They are 4.37 light-years from Earth. Proxima Centauri, our actual nearest stellar neighbour, is a red dwarf about 4.24 light-years away, orbiting the binary pair very loosely at a distance of about 13,000 astronomical units, with an orbital period of roughly 500,000 years. Whether Proxima is gravitationally bound to the pair or merely a coincidentally proximate object is a question that was only fully resolved in the early 2000s. It appears to be genuinely bound, though the binding is very loose. This matters because some proposals for reaching the Alpha Centauri system have focused on Alpha Centauri A or B rather than Proxima, since A and B are Sun-like stars around which Earth-like planets might be more straightforwardly habitable. No confirmed planets have been found around Alpha Centauri A or B. Those searches continue. The binary nature of the inner pair makes planet formation and stable orbits in their habitable zones challenging. The gravitational influence of the companion can disrupt or destabilize planetary orbits, depending on the orbital configurations. Some regions of stable orbit exist, but they're more restricted than around a single star. The full Alpha Centauri system thus presents multiple potential destinations at essentially the same distance, with Proxima be the only confirmed habitable zone planet so far, and the binary pair offering more Sun-like conditions but no confirmed planets. I want to take you back, now that we've walked through all the obstacles, to the question of why it matters. Not in the abstract, grandiose sense, the future of humanity depends on it and so on, though versions of that argument have been made, but in the more specific, more grounded sense of what reaching another star would actually mean, and what we would learn from it. The scientific value would be extraordinary. Proxima b, if it has an atmosphere, if it has a surface, if it has any of the conditions that on Earth led to the emergence of chemistry and possibly life, could answer questions that no telescope on Earth or in orbit around Earth can answer. The resolution required to image a planet's surface features, to detect the signature of oceans or vegetation or atmospheric chemistry that goes beyond what transit spectroscopy can reveal, requires being close, being in the system. Proximate, the philosophical value would be equally profound and harder to articulate precisely, but worth trying. Since the beginning of our species, we have inhabited one world, one planet, one gravitational field, one sky, one set of evolutionary pressures, one version of biology, one instance of whatever process produces minds capable of asking questions. Reaching another star would mean, for the first time, that life had crossed the interstellar void. That whatever it is that happened on this planet, whatever sequence of chemistry and physics and time produced something capable of wondering about itself, had extended itself beyond the sphere of its origin. That would be a different kind of event from anything that has happened before, not just for us. For the universe, if the universe is the kind of thing that tracks such events. Life reaching across the interstellar gulf would be, in the language of the long story of cosmic time, a new thing happening. Whether it's possible in a time frame that any of us will live to see, whether it's possible in a time frame that any human civilization will live to see, we don't know. The obstacles are real. The physics is demanding. The engineering is beyond anything we currently know how to do, and some of what's needed may remain beyond reach for a very long time. But the direction is clear. The problem is defined. The specific obstacles are identified, and the history of technology is a record of specific obstacles being overcome when sufficient ingenuity and effort were applied to them, sometimes on timescales shorter than anyone predicted, and sometimes much longer. Let's come down slowly now. The big ideas have been laid out. Let them settle. Here is the honest state of the question, as clearly as I can put it. Proxima Centauri is 24 light-years from Earth. It hosts at least one planet in its habitable zone, possibly rocky, possibly with liquid water, possibly with an atmosphere, though none of these possiblies have been confirmed. Our fastest current spacecraft would take about 74,000 years to reach it. The most plausible near-term approaches to dramatically faster travel involve nuclear propulsion, which could potentially reduce travel times to the range of centuries for a large crewed ship. Or laser-driven light sails, which could in principle reach Proxima Centauri in 20 to 30 years, but require engineering capabilities. A 100-gigawatt laser array, a gram-scale sail that survives interstellar dust at 20% of light speed, that are not currently achievable, and whose timeline to achievability is genuinely uncertain. The most ambitious interstellar mission proposal of the 21st century, Breakthrough Starshot, spent approximately $4.5 million over 9 years, funded about 30 research contracts, generated genuine advances in photonic sail materials and laser physics, and was placed on indefinite hold in 2025, with its future murky. The fundamental obstacles are not primarily political or economic, though both are relevant. They are physical and engineering, the rocket equation, the fuel problem, the deceleration problem, the interstellar dust erosion problem, the communication problem. Each of these has potential solutions that are physically plausible. None of the solutions currently exists as a practical technology. Building them would require sustained investment and effort over timescales that dwarf any existing human institutional commitment to a single project. This is the honest truth about reaching our nearest star. It is nearly impossible in any near-term sense, and genuinely possible in some long-term sense, where long-term means timescales that are hard to predict and may well exceed anything our current civilization can plan for. I want to leave you with one thought before the night ends, because I think it's the right thought to carry into sleep. The fact that Proxima Centauri is nearly impossible to reach does not make it less important that we think about it. In fact, I'd argue the opposite. The specific engineering difficulty of reaching another star is itself enormously informative, about the laws of physics, about the structure of the universe we inhabit, about the scale of the distances that separate stars, about what it means to be alive on one small planet and aware of others. Every proposal that has been seriously made for reaching Proxima Centauri has deepened our understanding of something. Orion deepened our understanding of nuclear pulse propulsion. Daedalus deepened our understanding of fusion rocket dynamics. Starshot deepened our understanding of photonic sails and laser arrays and the structure of the interstellar medium. The engineering studies done in service of an as-yet unrealized dream produced real knowledge, and that knowledge informs everything from power generation to materials science to our understanding of what lies between the stars. The dream is not pointless because it's hard. It is exactly as valuable as the specific knowledge gained in pursuing it, and the specific knowledge is substantial. And there is the larger thing, which is harder to articulate but equally true. The distance to Proxima Centauri, the 4.24 light-years, the 40 trillion kilometers, the 74,000 years at Voyager speed, that distance is not just an obstacle. It is information about the universe. It tells us something about what it means to be where we are, about the structure of the galaxy, the spacing of stars, the specific rarity or ordinariness of each stellar system embedded in the broader tapestry of the Milky Way. We live in a universe where the nearest star is 4 light-years away. That is the universe we live in, not 4 kilometers, not 4 light-months, not 400 light-years, 4.24 light-years. The gap is exactly what it is, and understanding it, really understanding it, in the full engineering and physical and philosophical sense, is part of understanding what kind of place this universe is. And understanding what kind of place the universe is, I think, one of the most important things any conscious being can do with the time it has. Close your eyes if they're not already closed. 4,024 light-years away, in the direction of a southern constellation you may never have named, a red dwarf star glows dimly in the dark. Redder than our sun, cooler, older in some ways, and more violent in others. Around it, in a tight orbit that takes 11 days to complete, a planet the approximate size of Earth makes its way through the habitable zone, bathed in radiation, possibly sheltered by a magnetic field, possibly stripped bare, carrying on its possible surface the possible conditions for the possible something that might one day be found by a possible mission launched by a species that is, currently, painstakingly, imperfectly, working on figuring out how to cross 40 trillion kilometers of cold dark space. That species is us. That project is ours. And it is harder than we usually say it is, and more important than we sometimes remember, and belongs to a future that is genuinely uncertain, but not genuinely foreclosed. Somewhere, perhaps, a material scientist is growing a film of silicon nitride with a reflectivity that didn't exist last year. Somewhere, a laser engineer is designing a new coherent array. Somewhere, a student is working through the dynamics of deceleration at relativistic speeds, looking for the elegant solution that hasn't been found yet. The nearest star is nearly impossible to reach, and so it has always been for everything worth reaching. Sleep well. And 4 light years away, the star goes on shining. Good night.